seminar of the European Non-Associative Algebra Seminar. And today we have the pleasure to have Laubie from University of Strasbourg. And he will talk about combinatorics of free pretty algebra and algebra with several pretty products sharing the Lie brackets. So don't hesitate to ask questions or put questions also in the chat. I think Paul will be extremely happy to answer them.
Yes. So I hope you can hear what I say, and I will share my screen. But since I'm not at my university, I cannot see Zoom and share my screen at the same time. Okay.
Yes, we can see. Yes.
Okay. So as Ivan said, I will speak about combinatorial description of free pre-algebra and algebra with several pre-brackets. So first, I will give some motivation and why I'm studying this. Then I will speak a bit about free algebra and operads. And then I will speak about two examples of operads. That will be the main character, the permutative operad, and the pre-operad. Then we will study coproduct of several copies of the pre-operad fibered by the operad. And finally, we will see how we can understand those operads using graph trees and using also the child relations that will appear at some point. So first, why am I willing to study those objects? Why? The algebra appear almost everywhere in mathematics. However, they are a bit tricky to study, right? Especially free algebras. It is still possible using Grobner-Kirchhoff basis. That's something that we may want to understand is the free algebras that live inside the free associative algebra. Because a well-known result is that an associative algebra is in particular a free algebra using the commutator, but we may want to give a description of the free algebras that live into the free associative algebra. Oh. Okay, so I don't know why, but I cannot.
You're able to move to the next slide?
Yeah, okay, I can.
No, I have Dominique. I have I can see part of the slide. It's not only black for me.
For me, it's totally black.
Okay.
Oh.
Paul, can you try to unshare and share again? Just because there is some kind of black rectangle on the slide. I mean, depending on the person, more or less. I mean, the size varies.
Okay, I will try to do so. Okay. Okay, I don't know how I do this. Oh, I see.
Oh, yes. Now for me, it's better.
Okay, there may be a black rectangle.
Yeah, a black rectangle on the right, but it's not covering the slide. So
yeah.
Is it better, Dominique, for you? I mean, you are like.
Yeah, it's okay, except two black boxes, but they don't hide the text. So yeah, it should be okay.
Okay, well, I apologize for the inconvenience, but since I'm not at the university, I have to use my small computer. So there may be some small bugs. So another motivation come from pre-algebras. Well, first I should give you the definition of a pre-algebra. So it's a non-associative algebra. However, the non-associative product satisfy a relation, which is written on the screen. So how this relation should be understood is that the failure to satisfy associativity is right symmetric in this case. It could also be left symmetric, but it doesn't change much. And they also appear in a lot of mathematical domain. So it appears in combinatorics by grafting trees, in geometry with flat torsion-free connection on a smooth manifold. It also appears in deformation theory, especially when we in deformation theory of operads. And we also know that the free algebra live inside the free pre-algebra. So a second question we could ask is to give a description of the free algebra inside the free pre-algebra. One remark is that we have the following diagram. So the free algebra embeds in the free pre-algebra and also in the free associative algebra. And we have a surjective morphism of the free pre-algebra into the free associative algebra. So what is this morphism? Well, in an associative algebra, the associator vanish. In a pre-algebra, the associator is right symmetric. So in particular, if we make it vanish, it is right symmetric. Because of this, answering the second question, we answer the first question. But to have an explicit description, we also need a description of the free pre-algebra. So I will speak a bit about free algebras and operads. So we give an informal definition of an operad. It is a mathematical object that looks like an algebra, but that encodes algebraic structures. So the one formal definition we can give is the following one. So an operad is a sequence of vector spaces, and each of those vector spaces come with an action of the symmetry group. So usually a right action, but it doesn't really matter. And we also have a collection of equivalent maps that are the partial composition. And those maps satisfied the following relation. So first, they satisfy the parallel axiom. So there is the formula, but it should be understood with the drawing. So what the parallel axiom is saying is that if I compose G in F, and then I compose H in F, it is the same as composing H in F, then G. Because the number of inputs change, if I compose G in F or H in F, then we will have some renumbering, but well, those renumbering are not really important, and we will ignore them most of the time. And the other relation that they should satisfy is the sequential axiom relation. So this axiom should be understood by the fact that if I compose G in F, and then I compose H in an input of G, it's the same as composing H in an input of G, and then compose it with F. So once again, we have some rewriting, but well, this is, we ignore those at the moment. So the vector space Pn should be understood as a space of symbol of multilinear map of arity n. The action of the permutation group should be understood as the permutation of the inputs. The partial composition should be understood as the partial composition in the correct input. And with this, we can understand an operad as a space of symbol of multilinear maps, which is closed by partial composition. Usually, we ask the operad to have no symbol of arity 0, so we don't want elements. And we also ask for the arity 1 to be reduced to the identity. So is there some question about operads? Right. Then I should speak about 2 examples. So the first 2 examples I will speak about are 2 very well-known operads, the commutative operad and the associative operad. So the commutative operad is pretty straightforward to describe. In each arity, it is a one-dimensional trivial representation. And if I compose 2 operations, well, it gives me the operation of the next arity. The way to understand this is, well, if I have an associative algebra and I have n elements of this algebra, the only way to compose them together is to multiply them. The order doesn't matter because the multiplication is associative, and the permutation of the letters doesn't matter because we are commutative. We also have the associative operad, which encodes the associative algebra. So this time, the space of multilinear maps of arity n is of dimension factorial n, and the action is the composition on the right. And why? Because, well, once again, the order in which I do the multiplication does not matter because we are associative, so we can forget about the parentheses. However, the order of the element does matter. So the permutation of the element matters. Right. So one remark about this is, right, the 3 commutative algebra and the 3 associative algebras are well known. So the 3 commutative algebra, it's a direct sum of the nth tensor product of V, quotiented by the action of the symmetry group that permutes the coefficient. And the 3 associative algebra, well, it is the direct sum of the nth tensor power of V without any quotient. Here I start at n equal to 1 because I'm considering non-unital algebra, since it doesn't always make sense to speak about unitary algebra over an operad. And the one observation we can do is that we can rewrite those 3 algebra using the operad. So in the case of the commutative operad, we can tensor the nth power of V by the arity n component of the commutative operad, and then quotient out by the action of the permutation group. And this will give us the correct vector space. In the case of the associative operad, we can do the same. So we tensor by the nth component of the associative operad, and we quotient by the diagonal action. And since we have the left action and we have the right action on the nth component of the associative operad, it will just give us the nth tensor power of the vector space. So from this remark, we can now have the following definition. If I have any operad, the 3P algebra pointer is given by the formula that we had previously. So it's a direct sum of the tensor product between Pn and the nth tensor power of V, quotiented by the diagonal action. And because I don't really want to write f of P, I will write P instead of f of P. Oh. So what we see is if we have a complete description of an operad, it also gives us a complete description of the 3 algebra of this operad. So now I will speak a bit about the first two operads that we will study. So the permutative operad and the pre-operad. So a perm algebra, it's an algebra which is associative and which satisfies the permutativity relation. So the permutativity relation says that if I compute x times y times z, it's the same as x times z times y. And because it is associative, the parenthesis doesn't matter. We can see that this is a weaker version of commutativity because we can make any letters commute except the first one. From this remark, we can see we can give a description of the free permutative algebra over a set of letters. And this is a span of the commutative words, with a marked letter. So the first letter is a marked letter that we cannot make commute. And the multiplication is exactly the concatenation of the words. From this, we have the really beautiful theorem of Chapoton and Nivernais that say that the permutative operad is causal. So I did not define what causal means for an operad here, but let's say it is a technical condition on an operad. And its causal dual is a pre-operad. Well, this theorem is a bit technical and it is not that technical to prove, but one needs to know causal theory for operads. However, it has a corollary, which is really nice. It is since the permutative operad is causal and we know its causal dual, because we know an explicit description of the free permutative algebra, it gives us for free a free description of the free Prélier algebra. So the free Prélier algebra over some letters is given by the span of finite non-planar rooted trees, such that the vertices are labeled by the letters. And the pre-multiplication is given by grafting the trees together. So here I wrote a small example. So I have the tree alpha beta, the tree ABC, and to compose those two, well, I graphed alpha beta on ABC, and I do the sum over all the possible way I can do that. So the first one is I graphed alpha beta over B, then I graphed it over C, and here I graphed it over A. And since the rooted trees I'm working with are non-planar, I don't have to choose where I am grafting alpha when I graft it over A. Here I graft it after C, but it would be the same if I would be grafting it before B or between B and C, because we don't put any order on the children of A. All right. Now I will try. Okay, so is there any question about this? I should maybe speak a bit about.
Yes, maybe a short question, Paul. Just because you said that in the case of the permuted operad, it's known that the causal is pretty. Are there other nice simple operas when you know the causal dual, or do you have a systematic way to compute that? Or
yeah, there is a systematic way to compute a causal dual of any operad.
Okay.
And it is explained in the book of Laubie and Vayet. And while you have to follow an algorithm, and it will give you the explicit computation.
Okay, thank you.
So here I should say how to prove this theorem. So the proof I'm going to, well, the sketch of proof I'm going to give is not the original proof, but this is, I guess, with the operatic tool we have today, it is the most straightforward one. So the first step is to get a quadratic reacting system. Oh, writing. For the operator term. The second step is to use the guess we have of the free term algebra to show that it is congruent, to show the congruence of the quadratic rating system. And the third step is we use the Ginsburg Caprana. So I hope I'm not misspelling it. So those two steps show causality and show that the guess we have for the free permutative algebra is the correct one. And the last guess allows us to describe the free pre-algebra. All right. Now, time for the coproduct of several pre-algebra favored by the algebra. So the idea is we want to describe the free algebras that live into the free pre-algebra. So one strategy could be the following one. So we can consider algebra with two pre-products that share the same Lie brackets. Then up to some modification, we would like to construct a differential D that we send the first pre-product to the second pre-product. And then we can hope that the two pre-products will kill each other in the cohomology and that they will give you the free algebra. So of course, this is not guaranteed to work, but in our case, it will work. So, oh, this is a bit unfortunate. Did I move the black square away from the?
Fine. I mean, they are still away from the from your presentation. They're still there, but
okay. I cannot make it disappear. I'm sorry.
Okay.
So at the operatic level, if I want to describe the the coproduct of two pre-algebra over the of two pre-operad over the re-operad, well, I have a presentation of the pre-operad by generator annulation. So I already say that an operad is something that took an algebra and that encode algebraic structures. Well, in fact, if we work in the correct category, it is literally an algebra. So we have a free operad functor that we give you the free operad over some set of generators. So we need to remember that in this case, the generators are symbols that correspond to multilinear maps. So here it is a symbol that corresponds to a multilinear map of arity 2, which has no symmetry. And then we need to quotient this by the relations that should be respected in the free pre-algebra, in any pre-algebra. So. And so this, we can say that this is exactly the pre-relation. So if I replace 1 by x, 2 by y, and 3 by z, I have exactly x times y times z minus x times y times z, which is the associator, minus the associator with y and z reversed, it changed. And thus, we have a really nice presentation of the coproduct of two pre-operad over the re-operad. And what is it? Well, it is quite simple because I just want two pre-products. So here I have the arrow and the triangle. Each of them should be pre-product, so they should satisfy the pre-relation. So I did not rewrite the relation, but it is the relation which is here above, 2 times, one for the arrow and one for the triangle. And this coproduct is fibered over E, so they should have the same commutator. So here it is, I'm just saying that the difference of the two commutators is 0. Well, from this, we can compute the first arity-wise dimensions. So we can compute them either by hand or using the software. So in arity 1, we are in dimension 1 because we already, I've already said that we usually impose that in arity 1, we only have the identity. In arity 2, I have something on dimension 3. Why? Because I can, I have the first pre-product. The first pre-product, but with the two inputs switched because I don't have any symmetry. The second pre-product with the two inputs switched. So here I'm of dimension 4, but I have a relation saying that the two commutators should be the same. So I'm using 1 dimension, I am of dimension 3. Sorry. In arity 3, well, we can compute the dimension and see that the dimension is 22. In arity 4, we can also compute the dimension and see that it is a kind of big number. But well, not that big, it is still doable. And what do we do when we have a sequence of numbers? When we check on the online encyclopedia of integer sequences if this sequence has already been studied. And in this case, we are lucky because we find something. It is a sequence of rooted Greg trees. And this is really nice because pre is related to rooted trees. And here I have something related to rooted trees. So I can hope that it is not a coincidence and that there is something to find here, which is the case. However, I'm telling you that this is a sequence of rooted Greg trees. I should define them. So a rooted Greg trees is a finite rooted trees. So once again, it is a finite rooted non-planar tree with black and white vertices, such that the black vertices are unlabeled. So they are not entries that we count in the arity. The arity is only given by the number of white vertices. And the second condition on the black vertices is that they have at least 2 children. So here is an example. We have the 3 rooted Greg trees with 2 white vertices. And those are the only one, since, well, if here I switch 1 and 2, well, since they are non-planar, it will give me the same tree. So now we can make this combinatorial object into an operad. But since I don't really want to work at the level of operad and more at the level of algebra, I will directly give you the definition of a Greg algebra once we have defined the Greg operad. So a Greg algebra, this is a vector space with 2 products. So the first one, the arrow, is a pre-product, and the second one is a commutative non-associative product. And they should satisfy 3 relations. The first one is the commutativity of this circle. The second one is the pre-relation for the first product, since I said that it should satisfy the that it should be a pre-product. And the last one is what I call the pre-relation, the Greg relation, sorry. And so if we look at those equations, we can see that the pre-equation is saying that the failure to be associative is right symmetric. While the second equation is the failure to satisfy the Leibniz rule is right symmetric. So we can see that those two equations are really closely related. However, here, like in the permutative and pre case, the causal dual will be more manageable. What I want to say with this sentence is that it will be way easier to describe the free algebra, sorry, over the causal dual than to describe directly the free Greg algebra.
Paul?
Yeah.
Paul, excuse me, it is Dominique here. May I make a stupid comment? Because you work with right Freely algebras. I guess your signs like triangles or greater than, they should point toward the left.
Ah, yeah.
You know what I mean? Because when I see your Leibniz rule, it's more or less your z acting on x and y. So you know what I mean?
Yeah, I see.
It's just a stupid notation comment, but I think it's somehow important.
Yeah, okay. So, well, I'm not really used to work at the level of algebra, so I may have made a mistake using this notation.
No, that's no mistake. It's just a notation comment. Sorry for that.
Oh, it's fine. So is there any comment or question about those Greg algebras? Okay, so if there are no questions, well, we try to describe the causal dual of those algebra. And here I will define a Schar algebra, which is in fact a Greg dual algebra. And once again, this is a vector space with two products, the dot and the arrow, such that the arrow is skew symmetric. The dots give us a permutative algebra. We have two nilpotent relations. We have Leibniz rule. We have a Leibniz rule, which is kind of hard to guess because one of the two terms of the right-hand side is 0. That's why this is still Leibniz rule technically. And the last one, which is a Schar relation. So I didn't use this name of Schar algebra, and this is a remark of Muriel Ivernay, who told me that the gas relation is really a Schar relation. Why? Because it is saying that to go from x to z is the same as going from x to y and then going from y to z. This is why I noted this with an arrow. The skew symmetry means that going from x to y is the opposite as going from y to z. And why we also have the permutative algebra and some nilpotency relation, because this is a general fact that the less relation you have in an operad, the more you have in its causal dual. And those algebra are quite nice because we can give a combinatorial description of the free algebra over this operad. And indeed, the free Greg dual algebra over a set of letters is a span of the commutative words over those letters with two possibilities. Either we mark the letter, same as in the permutative case, or we have an arrow from a letter to another letter. However, we need to caution by some relations. The first relation is the skew symmetry of the arrow, and the second relation is exactly the Schar relation. So here we can ask how the composition, what are the composition, and the composition are given by those following rules. So the first one is exactly the same rule as in the permutative case. So we concatenate the two words, and we forget the marking at the right. If we want to put an arrow between two marked words. Then we put an arrow from the first marked letters to the second marked letters. And if we want to concatenate a word with an arrow with a word with a marked letters, we forgot the marked point and we just have the arrow. All the cases give us 0. So if I want to put a letter between two words and one word already have an if I want to put an arrow between two words and one of the words already have an arrow, it will give me 0. And if I want to, and also the dot product is not allowed to forget an arrow. Instead, it gives me 0 and stuff like this. From this, we can show using the exact same strategy as in the theorem of Chapoton and Ivernay that this operad is causal. And why? Its causal dual is the Greg operad because we made it, so it will be true. And as a corollary, we have that the free Greg algebra of a set of letters is exactly the span of rooted Greg trees, such that the white vertices are labeled by the set of letters. And moreover, the operation, like the operation, is given by the grafting, and the new commutative product is given by attaching the two trees to a new black root. Is there a question about this construction? Okay. So now we are happy because we have a nice and beautiful operad which come from combinatorics. But this is not the operad we wanted to study in the first place. In the first place, we wanted to study the coproduct of two pre-operad fibered by the re-operad. So what is the link between this Greg operad and this coproduct? Are they equal? Well, this theorem exactly tells us the link between those two. So they are not equal. They are equal at the level of the combinatorial level. They are equal, but the composition are not the same. And in fact, what we have is that the inclusion of pre into the coproduct of two pre-operad, let's say in the first component, induce a filtration. And the Greg operad is exactly the operad we get by grading according to this filtration. And moreover, so here it is the wrong way around. So the coproduct of two pre-operad is a deformation of the Greg operad. So we say mistake. What do I mean by this? Well, what I mean is there is a family of operad indexed by a real number t, such that for t different to 0, we get the coproduct of two pre-operad, and for two, we get an operad which is isomorphic to this coproduct, and for t equal to 0, we get the Greg operad. So this is very similar to the Poisson and associative case, because we know, or at least it is known in operatic theory, that the associative operad is a deformation of the Poisson operad, meaning that we have a family of operad indexed by t, a real number, such that for t different to 0, I have an operad which is isomorphic to the associative operad, and for t equals 0, I have the Poisson operad. Right. So here we have a small remark. So when we have an operad, we can compute its generating series. So it is the sum of the dimension of the operad in arity n times t to the n. We need to quotient by factor n, but this is not important here. And here with the Greg operad, where we already said, oh, sorry. So here with the Greg operad, we already said that it was graded. So the Ebert generating series have an extra grading, so we have T, which counts the number of white vertices, which is exactly the arity. And we have also an extra grading Y, which is the number of black vertex. So with this formula, we may remark that if we set Y to be equal to 0, so it is the same as the combinatorial interpretation of putting Y equal to 0 is the same as forbidding any black vertex. We get the generating series of the rooted trees. So we get the Ebert generating series of the pre-operad. And if we put Y equal to -1, which does not have any combinatorial sense, but we have to do that nonetheless, we get some generating Ebert series, which is well known because it is the generating Ebert series. Quite nice because why putting a -1 in a generating series should remind us about the area characteristic of a chain complex. So we can hope that our strategy will work. Now, a quick remark is if we try to differentiate, well, if we set the differential of a binary product with no symmetry to a binary product which is symmetric, and we differentiate the pre-evaluation, which is what I've written here, we exactly get the Greg relation. So this is a simple computation. And to differentiate a composition of product, we use the Leibniz rule. So here I have the arrow composing the first arity with the arrow. And to differentiate that, I differentiate the arrow which is composed and the arrow in which I compose, and I take the sum. Here I have only 6 terms of the sum because 2 terms cancel each other since this product is symmetric. So I have one term with this arrow, and this becomes a circle with a dot in the middle, and the one with this arrow and this become a circle with a dot in the middle. But since it is symmetric, 2, 3, and 3, 2 can be switched, and they cancel out. So we exactly have the Greg relation. This means that we can define a new operad that I will denote Greg -1, which will be the differential graded operad, such that the underlying operad is the Greg operad and the differential is the differential I just defined. And we have a theorem, which is the cohomology of this operad happens to be exactly the Lie operad. So how to prove this theorem? Well, this theorem is a bit more involved than the other one. Well, to prove it, in fact, we can use the following thing. So we have a theorem of Dotenko and Koroshkin. That states that so the homology of the twisting of the pre-operad is exactly the Lie operad. So here I should explain what the twisting of the pre-operad is and why I want to. But what we do have is we have that Greg -1 embed in this operad. And since we have Lie that embed in Greg -1, then in the homology the only possibility is that the Lie operad already live in grade. All right. So this operad, this theorem allows us to recover the characterization of Markov because, well, I said that we wanted to describe the free algebra inside the free pre-algebra, but in fact, we already knew a characterization of this, which was given by Markov. And what is this characterization? Well, the characterization relies on a construction which is, well, a bit strange, because what we do is we consider the free pre-algebra generated by V, and we adjoint to V a new element of degree 1, and we quotient this by the grafting of this element onto itself. So why not? Then we set a new differential, which try to make this algebra into a differential pre-algebra, and the failure to be a differential pre-algebra is exactly this, which if we write it down in the using the notation given by trees, exactly give us this, which may you may which may seem familiar because this is exactly a Greg tree, and this is exactly the Greg tree with two wide vertices, which is not a rooted tree. And the theorem of Markov is the following one. Well, first, in degree 0, we have the free pre-algebra. Well, this is quite clear because we are adding an element of degree 1, and there is no way to make to reduce the degree. So in degree 0, we did nothing, and the free algebra is exactly the kernel of this of the differential. So we can exactly recover this result from the free Greg algebra, because here this is the free Greg algebra. In fact, it is just the only difference is instead of having an additional operation, we have an additional element. And so when I was saying that this was not the true motivation, well, we had some extra motivation. So the first one is the morphism from Lie to pre is already well known, and we know that this is an embedding. But here we described it in a very explicit way, or at least at the level of algebras, it is very, very explicit. We exactly know what happened. And in fact, those techniques can be extended to construct the morphism from the F manifold operad to the commutative pre-operad. So I did not define those operads, but a good way to think about the F manifold operad is the following one. So Lie algebra historically were introduced to encode the algebraic structures we get on a vector field of smooth manifold. And the F manifold operad will exactly encode the algebraic structures we get on Frobenius manifold, on the vector field of Frobenius manifold. And what we get is we get an extra commutative product which failed to satisfy the Leibniz rule, but the failure to satisfy the Leibniz rule satisfies the Leibniz rule. And one way of saying this is to say that the F manifold operad is to the pre-operad exactly what the Poisson operad is to the associative operad. And the issue here is that this operad is not quadratic. I mean, there is a quadratic integration, which is the Hertzing-Mann integration, which is clearly not quadratic. It is a cubic equation, which is quite tedious to write down. And so the techniques I've showed here can be extended to construct this embedding to the commutative pre-operad, which is a pre-operad with a commutative product and satisfying the Leibniz rule. And this one, so the F-manifold operad does not behave well at the operatic level. We don't have that many tools to study it. However, the commutative pre-operad behave very, very well, and we have a lot of tools to study it because it is almost as nice as the pre-operad, which is really nice. And yeah, and so those techniques allow us to show this embedding, and in a very explicit way, because it allows us to explicitly understand the free F-manifold algebra inside the free commutative pre-algebra. And so I guess this is the end of my talk. I've been a bit fast, I guess, but well, thanks for your attention.
Oh, thanks, Paul, for your nice talk. Are there any questions or remarks on that? I may start with one comment on the in the slide just before when you talk about applications. So here you study these injections of Lie into pre-Lie, and then this extension that you did. Are there other injections that you can prove using these techniques, or these are the two main ones?
Here?
Yes, you do F-man into pre-Lie. Are there other?
Yeah, I guess there are other. Okay, I guess those techniques they require a lot of structures on the operad.
Yes,
but I guess there are other operads that can be studied this way. So in my opinion, those are not the only one. I haven't used those techniques to show other embedding of operads, but I guess it should be possible.
And if I replace pre-Lie by post-Lie, what we could expect?
I don't know. I don't know. But we can expect those constructions to work with post-Lie. I don't exactly know what we want, what kind of embedding we would like to show with post-Lie, because in fact here, what I'm doing is I'm killing the anti-commutator in pre-Lie. So in post-Lie we have three products. So we have well, this is not a pre-product, but we have a non-symmetric product that can be cut into two pieces, either the commutator and the anti-commutator, and we also have a pre-bracket. So we need to know which one we wish to remove. So I guess if we remove the two skew symmetric one, we get the free commutative non-symmetric non-associative operad. But if we keep only two of them, I guess we can use those techniques to see which operad we get.
Maybe a good track would be to consider planar Greg trees and see what happens. No?
Yeah, I'm already considering those, and so I already know a bit what I will expect to happen with planar Greg trees, because we will have some objects related to the brace operad. The issue is the brace operad is not quadratic, so we cannot directly apply those techniques, but we can still. So when I say they are not quadratic, I mean, yeah, we cannot hope to have this kind of theorem, the theorem of causality or stuff like this. We cannot hope to have them, and we will have to find a description of the operad in another way. However, or to compute the dimension in another way. However, what we can hope to have is this theorem, the theorem about the cohomology. This one we can hope to have it, and I'm pretty confident that we have it, in fact. So I don't exactly know which opera the cohomology will be, but I'm pretty sure it will be concentrated in the group zero.
Are there other comments or questions? I think if not, we can thank Paul Laubie again. Thank you for your nice talk again. Maybe I can just hand in to the organizer of the seminar. Maybe they can tell us about the program for next week, or